All right, so what, did you have a question, Marissa, or were you,
Yeah.
okay, what was your question?
Okay, so number 39 is like using the band of stability. How would you determine whether an isotope is likely to be unstable?
Well, the band of, anything that's not on the band of stability is unstable.
If it ain't on that line.
Yeah, on that curve, yeah, the fat curve, yeah. Okay, hold, I think Thomas had a question first. I'm gonna go to him next. What was your question?
I don't understand how you did that problem where it's like, if they have like a carbon 14 or 5,700 years, how much of the original amount would be left after 17,100 years?
Every 5,700 years, half of it goes away. So after 5,700, it's half.
Just got the chart.
Sure.
Fourth is left after.
All right. All right. Let's do a little bit of it. Let's do some pictures here, okay? So here's our starting amount. The problem doesn't tell you how much there is. So I'm using this pi, okay, to show a starting amount. That fair enough? Now, this is the beginning of our time period. Okay, so we're going to assume our time period is 0 time right now. Okay? Alright, so this is a whole pi, so we got the whole thing at the beginning of our time period, right? Alright, the half-life of carbon-14 is 5,700 years. Okay? So at 5,700 years, half the pi is gone. Does that make sense? Okay. The second half-life is 5,700 plus another 5,700. That's the second half-life. That's 11,400 years. Okay? So in 11,400 years, half of this is gone. 1/4 is what we have left. Okay? Another half-life period of time is 5,700 years. 17,100 years. Does that make sense? That period of time, it's going to be half of this is 1/8. And if we went further, we'd have a thinner slice of pie, wouldn't we? But we never completely get rid of the pie. Yeah. In the next half-life, we'd add 5,700 years here, put that number here, and have 1/16 of a pie. Yeah. Okay. Jessica's next. No, she had her hand up way earlier. Okay. I'm not disrespecting you here. Okay. Honestly. Okay. Go ahead. Huh? Would you read the question? Tell me what you're asking.
It's balance the following equation. It's butane plus O2.
Now, did it give you the names or did it give you a structure? Okay. Guys, turn it down. Thank you. What physical state do we assign to the carbon dioxide? What physical state will we list for carbon dioxide? A gas. What physical state do we list for water as a product in a combustion reaction? In a combustion reaction, it's a gas, because combustion reactions create heat. So whenever you get water in a combustion reaction, it's a gas. It's not in other things, but it is in a combustion reaction. If it's a double replacement reaction and you make water, that's a liquid. But in a combustion reaction, when you make water, it's a gas. Okay? Yes. All the way.
Dang! Not even grasping.
I haven't finished this question now, so unless your questions are about this, let's hold your questions. Okay? Now we need to balance the equation. You list all the elements. Write your grid or spreadsheet. Count all of your elements on both sides. Remember, everything on this side over here is on this side of the atom inventory. Everything on this side of the equation goes on this side. So I've got 1, 2, 3, 4 carbons. Huh? Oh, well, there's 10 hydrogens, but not 10 carbons. So that's, you think you knew the rest of it then, is that right? I mean, I'll do them for you. Okay? Alright, so once your formulas are balanced, so when you predict the products of a combustion reaction, you already know what the balance formulas are. Okay? You've got the subscripts there. CO2 is always CO2, right? Water is always H2O. You don't change the subscripts. Once the formulas are balanced, you can't touch this. Okay? Yeah. Yeah, right. Okay? Somebody got it. All right. All we use for balancing equations is coefficients, or R coefficients. So I'm going to use a coefficient in front of CO2, and I'll change that to a 4. Also going to change the number of oxygens. See this thing right here? See? Well, I got my hand here. This is a wonderful tool, guys. Wonderful tool. It's called a writing instrument. Please don't fail to write stuff down to help you keep up with it. I've been doing this a long time, and I still write it down to keep up with it. Okay? So write it down to keep up with it. It'll help you a lot. You won't make those silly little numerical mistakes that cost you lots of points on a test. Okay? So 2 times 4, 4 times 2 here is 8 oxygens there, plus the 1 oxygen here. So we've got, 1. So we've got 9 oxygens. Okay? So we're going to change this to 9. So we say we're going to save oxygen for last. The next thing we want to balance is the hydrogen. I've got 10 on this side and 2 on this side. This is the species that has the hydrogen. Remember, I can't touch those subscripts. I can only put coefficients out here. That's going to give me 10 hydrogens, but it also changes the oxygens because the coefficients apply to everything in the formula. So we're going to recalculate the number of oxygens. 4 times 2 is 8. 5 times 1 is 5. That gives us 13 oxygens. All right. So now I have that situation that occurs often, particularly in combustion reactions, where I've got an odd number of oxygens on one side and an even number on the other. And I think I heard Shane start to say how to handle that. Everything but the coefficient in front of the oxygen gets multiplied by 2. Please remember, the implied coefficient here is not 0, it's 1. So we're multiplying this 1 by 2. This gets multiplied by 8. This gets multiplied by 2 to get 8, multiplied by 2 to get 10. And we recount everything. So this is 8, 20, 8, 20, 26. So now that I need 26 oxygens, I need to multiply this O2 by 13. That'll give me 26 oxygens, and we're done.
So the final answer is what?
This is the final answer. Yeah, the whole thing's the final answer. You have to. Amber, somebody else had a hand up a minute ago.
I did.
Was it? Okay, okay.
Okay. It's 65 and 66. Oh, it says, okay. When magnesium chlorine combine, what holds the compound together? Then 66 says when sulfur and chlorine combine, what holds the compound together? Hold on. Is the answer is that opposite charges called electromagnetic attraction?
That is the case for magnesium and chlorine, but not for sulfur and chlorine.
Okay.
Okay? So magnesium is a metal. Chlorine is a non-metal. So when magnesium combines with chlorine, magnesium is going to give up electrons and chlorine is going to gain them. So you're going to have two oppositely charged particles. The opposite charges are what holds magnesium chloride together. Okay? Sulfur, on the other hand, is a covalent is a non-metal, and chlorine is also a non-metal. So they combine by sharing electrons.
Okay.
But what holds them together is the stability of having a full valence level of electrons. Okay? And you can kind of see that when we go through that whole process of the electron dot notation and sharing. Remember,
The ability of what now?
of getting a full valence level of electrons.
What number is this?
I don't know. What number is this, Amber?
66. That's the answer? This is the answer?
Okay, so notice,
Ability of getting a full valence electron.
no, full valence level of electrons.
Oh, level of
All right, so sulfur and chlorine then, if they share electrons in this way, then they're both, every element here is going to have 8 electrons in the valence level. Sulfur has 8, 1, 2, 3, 4, 5, 6, 7, 8 because it shared 2 electrons. Chlorines have 8 because it shared 1.
Okay. And how is single bond formed? Is it by hybridized orbitals? Or
No, it's simple. Actually, simpler than that. Single bonds are formed by overlapping hybridized orbitals, which is also means that they're sharing electrons. Single bonds are formed by sharing 2 electrons,
okay.
and those 2 electrons come from hybridized orbitals. So you're also overlapping 2 hybridized orbitals.